So once we have done all these analysis, we have to validate, because if you do this overfitting, you cannot trust, or you have to check that you do the overfitting. And you have to do different data set for this checking. So one part is of the data is split into the training data. Then while training, in the training iterations, you use the validation data. And then finally, to verify that it's actually doing and not overfitting, you test it using the testing data. There are different splitting strategies. You want most of the data for the training, some part on the validation, and then usually the testing is the least of the data amount. There are also strategies if you have very little data, that you can have some kind of sliding window principle in selecting validation and testing data to get to expose the training to more data than you would have otherwise. Once we have done the whole analysis, we have to do some, this one came a little bit strangely. I think I must have omitted a slide somewhere, but that was strange. Okay, anyway, we have done some analysis, and now we have to decide, what do we want to do, qualitative or quantitative analysis with the data. And the qualitative part is to use the metrics in a visual feedback, so you can see, you display the metrics with some plot or with some 3D rendering or something like that. You can also use it as to compare the expectations as a first selection, and also see in the data, are there artifacts included in the output from analysis, from experiments. Naturally checking if the shapes of the items you have segmented, if they are correct. That's a very important thing. And for that, it's usually quicker just to do this qualitative assessment. Afterwards, when you know you have the correct ones, or that they look sane, then you can start doing the quantitative analysis. Also, same thing is about the distribution and the orientation of the samples, if that makes sense. In the quantitative case, we want to calculate the whole specific shape, distribution of metrics in the sample. And we can see that there is a relationship between analysis parameters and metrics, and that can be seen in, for example, in this example here, where we have an algorithm for analyzing images, where we get in the raw images into a Gauss filter, and the filter has two parameters, sigma and how many neighbors. These are parameters that you can tune, and that will also have an effect on how you work, how the analysis will work. The result goes into thresholding, and there it's important to play with this threshold value, how it's set. And that really has a great impact on the analysis afterwards. And then afterwards you do your analysis, and that is the the quantitative output that you want to look for. So what we have to do is to do a parameter sweep on one or several of these parameters, and see what happens when we sweep them between, say, reasonable bounds. If you look at the histogram, you see that the threshold is beyond all peaks in the histogram. There's no point in putting a threshold there. So that can be judged qualitatively, setting these limits. And here we can see that we have some, I think it was a bone data set, was segmented in different ways. And you can see that the volume, it varies a little bit. So you can see the trend line, how the volume varies within the data. This gives you an indication that how the segmentation is working at different levels. You can also look at it with different kinds of graphs. So you can have this intensity plot or density plot, or you can have the violin plot, giving you more the spread, kind of a histogram within each category. Here we look at the volume again, but here we can see the orientation, that it's in the beginning. Here it's very high density in the upper part, but when we go to 9,000, all of a sudden there is a dropout down on a negative orientation. So something wrong is happening with the data. You can also see that the violin here is getting pretty fat in the bottom. So what we need to do is to run a sensitivity analysis, and in control system, sensitivity is defined as a change in the input value should match the change in the output value. And typically it's defined as change in metric divided by change in parameter. And usually it should be unitless, possibly in something, but if you look in image processing, it's not a natural analysis to do, because you have a threshold which is in the unit of intensity, and that you relate to a volume which is cubic meters. So the sensitivity unit would be volume per intensity, and it's a little bit strange metric. So what we do instead is to look at a practical sensitivity analysis, where we have the maximum value in the metric divided by minus the minimum value of the metric, and that's divided by the average value, and that can give us a good metric for the sensitivity analysis. Looking at the object count in an experiment, you can see that okay, it's going down, down, down. We want a small value that is little that it's little sensitive, and then at some threshold, probably around here, you should reach a minimum, and then we go up again, and then the object count is sensitivity is too high. So you see clearly where we have the best threshold in this plot. Now, if we start comparing more different parameters at the same time, we can see that some has high sensitivity is going down towards the middle, so that would be the count. But on the other hand, the volume and the count, no, the anisotropy, they have a peak at the same spot. So now we have to do something with this contradiction. We want to have very low sensitivity, but that is cannot be fulfilled in all of them. So now is the question, which metric is the most important? In this case, I would say that the one that fluctuates the most should probably have more focus, or maybe we should change something that makes all behave in the same way. Also, you can see that they're very low sensitivity to these compared to this one that has a pretty high, large dynamic in sensitivity. So I think we should probably try to tune against the counts in this case. Now to look for the reproducibility, that is what we always strive for, that in the publication, that the experiment should be possible to reproduce. And there are two parts of it. One is the analysis that should be possible to be performed by anyone, anywhere. That means there shouldn't be any platform dependence on the analysis. So the computer you use, or which software in principle. Well, the software is then a little bit tricky because at some point you have to rewrite the algorithms if you change the software. There shouldn't be any proprietary or in-house algorithms that are hidden, because then no one can really reproduce. There shouldn't be the magic clicking and tweaking or copying in the process, because that is really hard to reproduce. And ideally, there should be a single, say, major script that is taking the images in and produce the publication ready plots. So you have the whole workflow controlled in a single script. Then in the measurement side, you have to look for that there's no sensitivity to mounting or rotation. Or at least the analysis shouldn't be sensitive to that you have done it. Then sensitivity to noise, hopefully, but that means the noise should be reduced to a minimum. Otherwise, you have usually a hard time of working. And also dependence on exact illumination. Extreme case is if you have pretty strong headlight shining on one side, as you see on me right now. I have the window on my left side. Does the analysis behave differently if I would have the window on the right side? Would I get different results? And that should be made in a way, the experiment should be made in a way that you don't need this, but depends on your setup, if you can exclude it or not. But if you have a dependence on the illumination or mounting rotation, then you have to just describe it well so people can reproduce the same thing. If you do the reproducible analysis, you need to run it as some kind of script, and in most languages you can do it. For example, you can have a Python script which you call either on the command line, just calling it with Python and file name, or in the Unix systems, you can even make the file itself callable directly by using this so-called shebang line in the top. If the system doesn't recognize it, then it's just like a comment. So then you have to possibly have some input arguments to the file, and then you call your analysis function. You can do the same in MATLAB, ImageJ, and R. You would probably have some, this would be corresponding actually to a Unix script still, a bash script, but the similar thing could be done in a script on Windows. So this is a little bit straying away from the concept of not being platform independent, but the main thing is that you have some loop or something going across the analysis script. Here we would call MATLAB from the command line with some call line. This would be running the same thing on ImageJ, or using an R script would be another way. But right now we are mainly working with the Python, so this is what you would get. There are also ways where you would maybe do system calls to a C code that you have written, but that's another way. But you can do that also from either a bash script or a bat script, or what you would like to have. So now let's leave the whole thing of reproducibility to some point, and go over to a more technical detail, and that is unit testing. So it's a piece of that is very commonly used in software engineering. It also actually supports the reproducibility. And the idea is that when you write a program, you want to make sure that it actually does what you want, and not only head on just go straight to your problem, but you want to break down it into smaller sub pieces that you verify that they actually do what they want, what you want. And this has now been formalized in something called unit tests, and you can have them in most programming languages. It says here that it has built-in support for automatic testing and reporting in all these languages, Java, C++, MATLAB, R, and Python. Almost true. C++, there are libraries that you can call, and they're actually Google Test, for example. If you work with the graphical user interface libraries, Qt, there is an integrated part of unit testing in that. But in the language definition, there is not yet unit testing integrated. In this sense, there is a very interesting paper. Actually, there's a misspelling on that one. Sorry. No. Yeah, let's fix that later. Anyway, an interesting paper about how people handle error handling and how do they analyze their code. It is in Nature, what's it called? Nature Data or Nature, yeah, some Nature publication at least. It's actually good reading, giving you the idea of why testing and why a system may fail if you don't do it. The design of unit tests is, first of all, you have to divide your code into several functional blocks, and then you have to define what to test. First of all, each part should be tested individually, and you should also be able to take out one piece and put another one in the same spot, and it should produce the same result. And that makes it easy to update and work with the code. The entire path should also be tested, so that would be integration testing, where you have several libraries that combine into the final analysis task. And that is a way to detect if there is problem in the integration between different libraries. How to test is, first of all, you want to test the happy path. So testing what you expect the code to do. That is important that works, because otherwise there's no point in having the code. But the other side of it is to provoke your code. So sending wrong information to it and see how it behaves. And that could be some kind of error handling, getting a warning message, or throwing exceptions. But it's important that you report some kind of error messages in either as exceptions or in error code that returns the function return. Ideally, you should test the data with real data, but the best way is probably to do simulated data, because then you have the ground truth of input and output in your test procedure. And important is to think about that unit testing is only as good as the tests you write. And for that, there are even tools that check the test coverage, seeing how much of a code is actually covered by the test you perform. So let's have a function. We have the function count voxels, and we would like to write a couple of tests. One natural test is checking that count voxels of an empty image is 0, and there are 0 voxels that are non-zero in it. Good. The other one is empty 3D. Then it would be the same thing on the 3-dimensional. If we now would have a diagonal of ones in a 3x3 image, that would produce 3 voxels, and that should then produce a 3 here. And this assert is in Python is the function or the keyword used for the unit test. And if assert gets a false, then it already writes out an error line or warning line that this test didn't work. And then you write a couple of these tests on the data on your function and run it through and see what happens. So let's look at the unit testing of this data, of the function of shape analysis. First, we have the main function. That function can be split into 2 sub-functions, component label, which can be separated tested, and analyze objects, which takes the information from the component labeling. And analyze object, that can be split down into another 5 different sub-functions. Count voxels, count center of volume, count shape, calculate shape tensor, calculate orientation, and calculate anisotropy. Those are the smallest units of that are tested separately, and each can then have its own set of tests. In Python, we can use a test framework called PyTest. So just import PyTest. And it's good if you have larger projects to use this library. You can make specific tests for each module, and you can also run these tests every time you update the project. That, of course, is easier if you have an automation in the routine. Just to look at how other people are doing it, we can take a look at testing in scikit-image, and here we can see the watershed test function, where we have watershed 1. Then we have some data in. Apparently there is 1 single object in it, and it gets 1 in like this. And so we have the markers. And then afterwards it checks if there is a difference between expected and out, and then we check, okay, is there error less than some epsilon? Probably the epsilon here should be a 1, I would say, because there shouldn't be any difference in them. And that would be the test for this simple case. So you can see that there's a lot of code to write when you do unit testing, but see it as a way to help yourself to avoid mistakes in the future. You can also see different other ones. Just have to go to GitHub and look into the test code for scikit-image. What you also can do is to use something called doc tests. Then you refunction the function documentation into a test. So you can have here, you have this applied hysteresis threshold, where you have a starting comment, and in Python functions, you can have this comment to use as a help, but you can also add these examples where all these signs here indicate that we have a test going on. So image with this information, apply the threshold, and the output of that should be this. If it fails, then it will tell you, and otherwise it's fine. Oh, that wasn't meant to. So in Jupyter is a little bit more difficult, but it's also possible to use these doc tests inside of the Jupyter notebooks. But for that, we need to write some little extra code. So this auto test function helps us. It's a kind of a helper function that helps us to call the unit test code in the notebook cells. And then we add with this magic command, add execute auto test on this function here. And when we have this function, we have the documentation and say that the function should add 5. And if we did some typo, we did here instead plus add 7, then the unit test would complain directly and say, well, it failed. We expected 10 and we got a 12. So that already tells us back that we did a mistake. That's pretty good actually as feedback when you do your coding to do this kind of checking. A little bit more complex would be to use some kind of labeling function where you have, again, the unit test, we call it, and that should result in different arrays as output, and then we can see what happens. And the first run, we have everything very nicely, and one of them apparently here failed. There was some mistake in it, and see, I don't see why it should fail. But apparently there is something wrong in it. I don't know why. Let's execute it again. Probably there is some error ups in. That is okay. That is okay. And the last one. Looks like it's okay. I can't see really right now why it's not working as it should. Nope, I can't see right now why it's failing. But you can see that it should be able to catch different mistakes in your code. So you can always run this kind of experiment. Test code within your writing. So it's a good style to work with unit test. And then in MATLAB, if you prefer working in MATLAB instead, there is also a unit testing framework for that. Personally, I haven't tried it, so I don't know really how it works. In C++, you also have different unit testing frameworks that allow you to run your tests on the code. But in the first run for many of student projects, PhD projects, if you don't know C++ from the beginning, it's usually not worth the effort of starting writing the C++ code. Or you can see a really huge time benefit in it. But for the beginning, I think Python is serving you all pretty well to start with. Now that we have written all these tests, we can start taking it even one step further, and that is to do test-driven programming. So that means we start defining what we want to do in the code, writing some kind of, call it, requirement document. Based on that document, we start writing the test code, and that test code could be something like shape analysis must give as anisotropy of 0 when we input a sphere. It must give center of volume within half a pixel, and it should be possible to run it on 1,000 by 1,000 image within 30 seconds. Those are our criteria on the code. And then we can write our tests, and then we start implementing the code that does it. And once all these are fulfilled, we are happy. And that would be the code has finished in a good way. this is a kind of reversed way of thinking, and it's used in larger software projects. In the normal small project, maybe it's not really the approach that we're going for, but it's anyway good to have written the unit tests more or less in parallel when you develop a function. Yet another step up in the whole workflow is continuous integration. And that is that when you're working with repository, that every time you commit changes or push changes to the repository, it's automatically running tests on the data. And actually, these lecture notes, they are also verified using a framework called Travis. And that checks if all the slides are correct. Right now, it's actually gives a fail because I have changed the Python versions in what I'm doing and what Kevin did the years before me. So, and I haven't actually updated that part. So that's why it's currently crashing in the test. And this is actually done in projects like Scikit-Image 2. In my own development, I'm using a different framework called Jenkins. And that actually tells me the status of my current development that I'm running on. I can actually have tests on different platforms, and you can even see here the status of the different build servers. So I have building on Windows 10, I have building on Ubuntu 18.4, I have building on Mac OS 10.14, and every time I do some changes in my code and send it up to the server, then these build machines, they're starting building, and half an hour later, I get the result, good or bad. And then I can look it back into log files and check, okay, oh, that didn't work on the build system. And so that's a very useful tool. And you can even, in this build, you can even also call the unit tests and make sure that the unit test also execute in the correct way. So now let's leave the software engineering and go back to the, say, beautiful part of the publication, bringing out the message. And a very important thing in that is to do visualization. And often if you have big data, it's difficult to visualize, in particular if you have multidimensional data to show. Up to 3 dimensions is okay, but already 3D visualizations, they're more for qualitative use to get an idea how things are distributed. Tables is a way to show the data, not so reader friendly mostly. It's good if you want the details, but to get a quick idea of trends in the data, you need to plot it somehow. And with that, you have to decide what is the purpose of your visualization. You can visualize data for different reasons. The one is for yourself, so understanding and exploring the data. In that case, you have a very small and known audience. It's you, your room, your office roommate, or it's your professor, and all they know what you're talking about. You don't have to explain very much. That's a very technical way of visualizing the data. You need it during your research process, but once you have come up with your results, you shouldn't take those plots, but you need to present the data in a way that can be digested by your audience. And often it's a wider and unknown audience. So it could be a reader of a paper, could be someone listening to your presentation. And in that case, you can, at the best, expect a general understanding on your topic. And also what kind of medium you have to present on, as if you have a live presentation, you have pretty high amount of control. You can interact with the people that you talk to, and they can ask questions. So then you don't need very much detail in your plots. Then you don't even want high detail, because that would clutter and distract the people. They start looking at every little detail you have plotted up. Then you want a very, say, reduced plot, showing the information you want to show, but the rest you give by talking. On the other hand, if you have a written document, like a paper or an email or something, then you don't have very much control of how the information is conveyed to the audience. And with that, you need to add a lot more information in the plots. These thoughts, they are very nicely introduced in the book that I'm referencing here by Knaflik, which you can get through the ETH library. Of course, as I said, you shouldn't take the plots from your exploration phase and bring them in directly. There are too many plots. You probably have seen them yourself in publications, in presentations, that are telling my data is very complicated, and no one understands exactly what you want to show. Also, I know how to use this and that toolbox in any environment, MATLAB, R, Mathematica, Python. And also, when you start using different statistics programs, the default plots are not very nice. They're really bad, actually. And I think the worst plots you can produce are the ones you get from Excel. They're really horrible. And I actually recommend you never to use Excel as plotting for publications. It's really horrible, and you have no control. You cannot do anything useful with it. And also, good visualizations, they take a lot of time to produce, to think through what is the message you want to bring to the observer, and also highlight the things that are relevant within the data. So it's worth spending some time, because in the end, your message will get out easier. So how to improve? First of all, you have to define what is your message. And then you have to critically ask yourself, does this graphic really communicate this information clearly? And next question is also, actually even bringing back to the original question, is a graphic really necessary to show this? Does every line or color in my plot serve a purpose? In that way of thinking, you can kind of pretend that ink is very expensive, and you don't want to put too much stuff into your plots or graphics. That can be more misleading and confusing than helping the reader to see what you want to show. So again, here is the link to Knaflik's book, and there is a blog entry from a guy called Few, and he is also arguing, of course, you can make beautiful graphs. You can spend hours on doing it, but there must also be a point. And of course, you can bring the same message with less effort and less beauty. But if you can actually tell more with the beauty too, or highlight the information in a better way, then of course it's useful to do beautiful. And that is what he is discussing in his blog entry. Some simple rules when you start doing is never use 3D graphics. Unless you want to be misleading. So this is really a horrible example where you have these cones, and Here you can start thinking about, is it the cone volume that we are looking at? Is the cone height? Is it a cut surface or whatever? So you really see bad examples like this. Also pie charts, depending on how you use them, they can be very hard to interpret. Sometimes it's better to do a bar graph showing some trends because you can see the trends better. Only if you really want to say, out of 100%, I have this and that. But yeah, you have to motivate the pie chart pretty well. Background color should always be white, not light gray, because then you get a different highlighting. I know in my lectures, I have gray behind my plots. That's because I couldn't convince the notebooks to do anything else. I would like to have it white, but somehow I couldn't convince the templates to give me white. Then also use color palettes, which are adapted to human visual sensitivity. So you can play with intensities, you can play with colors to get the contrast you want, but also bear in mind that some people are actually colorblind and they can't distinguish between different color combinations. And that also brings into using these colors and transparencies in a smart way to bring the results. So let's look at an example. And here until now we have been using matplotlib a lot. And this is yet another. We have been using Seaborn, we have been using matplotlib for plotting. Plot9 is a package that has been inherited from the R language that is working according to a different paradigm in visualization. And so let's have some data. We have here some random dots with some trend in it. Usually the first plots that the system provides you is usually not good enough for bringing out a message to some readers or listeners. So what we need, we have to add some more decorations, and that would be that we have X is weakly correlated to Y. We have added some more labels here. We have a trend line even with confidence band of this trend line. So then we start talking about more information that guides the user's interests and understanding. And then it's also a question, how well does my graphic communicate my message? If you have this kind of data, you see just a bunch of dots. It doesn't really give you an idea, particularly not in the black area. You see that there is spread between X and Y, but you don't see how much this spread is. So what we can do now is to, let's hope this one is working. No, it's not. I have to go back. Sorry for that. Here. So this should be it. So let's reduce, and now we can see a different interpretation of the same data. And here you can see that there's very sparse data amount, and in the middle you can see that it's really intensifying, getting more dense, and in the very middle you have a very high count. So this plot shows much more about the data than the previous one. Now I've actually forgot to bring in a title, but that's a small thing. Now it's more about focusing on how the data is presented. And let's go on and see what we can do. Otherwise, we can also work with these isobars. Isolines is another way of showing it. And the important thing here is you start seeing here that I have the plot command and then plus different features. And this brings us into the grammar of graphics, and there's a way of bringing down the visualization into different building blocks. And grammar in general is a set of rules for constructing and validating a sentence. It also gives the relationship between different words in the sentence. And this kind of way of building up has now also been applied within the visualization. And we can express the graphics as a sentence, and the elements that we have within this graphics are the words, and we want to compose them in an easy way. An important work describing this is a book called Grammar of Graphics, which is also in the reading list on the top. It builds on earlier work on how to build up these grammars. In Python, we have this ggplot library that I already mentioned. And otherwise, you can also still use matplotlib, maybe not with that same grammar logic. If you want to work more in detail with matplotlib, I recommend this matplotlib cookbook, which you can get from the ETH library, I think only through the Safari environment. So you can only read it online, unless you buy the book, which is, I think it's about 15 francs or something, 15 or 20 francs. I think it's a pretty good book, gives a lot of ideas how you can visualize different things. But sometimes it can be pretty complex parameterizations that you need to do, and that is what ggplot2 can help you getting over. So let's looking at some plot here. We have this nice plot, and let's break it down into the grammatical components. And oops, yeah, there it is. Here we can break it down. We have two variables that have mappings to axes. We have some points. In this case, I did some coloring. You can also have different glyphs on the markers, if you like. Next level is to having the coordinate system. And finally, we have labels and annotations on the data. And altogether, they build up the whole effect. So, if we go back a few slides, let's go back to, yeah, this one. You can see here is the data mapping. Then it tells what to do with the points. Here I actually add a new element, a plotting line, telling how the coordinate system should be plotted. This is a theme, how to bring in the fonts in the labels. And then there are some guides as well. So this brings up the whole design, and you can even go back one more to this one. You can see here again we have the points just plotted as a scatter plot. Then you have a smooth line as a geometry component. And here now I added also labels. I could also have X and Y labels if I like. Setting the font size is this one. So here you have it split up in different components, and it's not that nice. You can do the same thing actually in matplotlib, but it's not that accessible as it is in the ggplot. But it's I think ggplot is probably matplotlib is probably the faster plotting library. I've noticed also that, for example, Seaborn is very time consuming when it's bringing up. It's bringing very beautiful plots, but it takes some time for them to be generated. It's also depending on how you want to work with how you're generating the plots. If you, in a long iteration, want to generate a plot for each occurrence of something, then you may want to go for something faster, but then you're also not in the presentation mode yet. And then it's more about just bringing information for your exploration. And that brings us to the end of today's lecture. I must confess, I'm definitely not a statistician, and this is not a statistics course, but I hope I gave you some introduction into what kind of tools you have to work with in statistics. If you have questions or concerns regarding statistics, I have heard that there are some free consultations about about statistics from real statisticians, and usually they tell you, please give me more data because this is too little, or you have done the analysis maybe in a little bit wrong way or something like that. Not for sure, but who knows? Maybe you did it right. But often you get the message, more data, and more experiments, more something. Simulations, they are very useful in different parts. One is for the parameter sweeps when we want to analyze how different functions in our analysis works, but also when we do unit testing. And the important thing is also then for the reproducibility that you actually have a stable code base that you work on, which a unit test is a very helpful tool in that sense. And that brings us to the end. And one more thing, by the way, let's see. Today's exercises, I only recommend you to look through this data set on Kaggle. It shows how an experiment is done. I wanted to transfer this NIME exercises into a Python notebook, but I realized that there's very much stuff there that is related to the pandas data frames. And I think it's better if you do this exercise when I have introduced the data frames, which I think I will do next week. So there will probably be a little switch of these two lectures, scaling up big data and imaging with multiple modalities. So this one will probably come next week instead. And then I will also introduce pandas, and then you can do these exercises. Another thing is how you work with the exercises. Right now, there is not much time, or actually both Stefano and me, we haven't got much questions regarding the exercises. So what we were thinking about, maybe if you want to, so some of the exercises, they are more exploring, seeing how things are done. And some exercises actually have some questions within them. And if you want, we can prepare a repository that where you can upload your solutions, and then we can maybe discuss around them, and other people can see what you have done. So it's like a open solution of these exercises. We are trying to follow up also with bringing solutions where it makes sense. And well, so please, maybe you can on Slack or on email say if you want this kind of exercise workshop in that way. And we can also, if you upload, we can also comment what you have done or how you can do it instead, etc. Yeah, I think that was all. So I'll stay online a little more. I see I have one question at least to take separately. So if there are other questions, please stay and we can organize who is coming in which order. So thank you for this week, and